Welcome, dear learners. Welcome to the course Quantum Chemistry. We are now discussing the hydrogen atom problem in part 1. The contents of this module are the hydrogen atom problem, its description, the Schrodinger wave equation in spherical polar coordinate, separation of variables, the r, theta and phi equations, complete solution to phi equation and complete solution to theta equation. First of all, the hydrogen atom problem. The hydrogen atom is the simplest atom, which is a three-dimensional system comprised of an electron and a nucleus. The nucleus of the simple hydrogen atom is a proton. For any other isotopes of hydrogen, we can use the center part as the nucleus. So simply, for every isotope of hydrogen atom, it consists of two particles, that is one electron and a nucleus. The Schrodinger equation for a hydrogen atom can be solved exactly. This means the hydrogen atom problem is an exactly solvable quantum mechanical system. Now, we are describing the problem with the help of a pictorial representation. Consider an electron at a distance r from the center of the nucleus, and this electron can travel in any direction along x, y and z axis. This is the situation. This electron is under the influence of positively charged nucleus. Hence, there occur a potential energy of attraction between electron and the nucleus. Such potential energy term is theoretically equal to VR equal to minus Z square divided by 4 pi epsilon 0 R. Here, Z represents atomic number term, and for hydrogen Z is equal to 1. And for hydrogen-like systems, it can have different values. For example, if we are having helium plus, it is also one electron system where we have to put Z is equal to 2. VR simply means that the potential energy term depends on the spherical polar coordinate variable R only. From this equation, it is clear that the potential energy depends on the variable R only. And here, the term epsilon 0 represents the permittivity parameter. Therefore, VR is equal to minus Z square divided by 4 pi epsilon 0 R. And again, E represents charge of the electron. Now, the hydrogen atom problem has Schrodinger wave equation, which can be solved exactly. We have the Schrodinger wave equation in its general form as Hamiltonian psi is equal to energy into psi. We know that the Hamiltonian operator H hat is a total energy operator. It consists of two parts. The first part being kinetic energy and the second part being potential energy. The kinetic energy part is like this, minus s cross square by 2m del square, where del is the well-known Laplace's operator or Laplacian operator. And in Cartesian coordinate system, Laplacian operator is given as del square equal to dou square by dou a square plus dou square by dou y square plus dou square by dou z square. So, this part represents the kinetic energy, and the second portion V of x, y, z represents the potential energy of the system. And for the hydrogen atom problem, we already studied that V x, y, z is equal to VR, that is equal to minus Z square divided by 4 pi epsilon 0 R, that we learned in the previous slide. The Laplacian operator is this, and this is the Hamiltonian operator, corresponds to the Schrodinger wave equation of the hydrogen atom problem. Now, the Schrodinger wave equation for hydrogen in Cartesian coordinate can be obtained by putting the value of the Hamiltonian operator in H hat psi equal to E psi. Thus, we are getting the Schrodinger wave equation in Cartesian coordinate as dou square psi by dou a square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into e minus v into psi is equal to 0. This v can be represented as Vr for more convenience. Vr means the potential energy depends on R. Therefore, I can put Vr. So, this is the Schrodinger wave equation of hydrogen atom in spherical polar coordinate. It should be noted that the hydrogen atom problem is a two-particle system. What are the two particles present in the hydrogen atom problem? It is nothing but an electron as well as a nucleus. If two particles are present, it is more better to express the mass of the entire system as a reduced mass. If m1 and m2 are the masses of two particles, see for example, the first particle being electron, so its mass can be represented as me. The second particle being nucleus, so its mass can be represented as m1. So me m1 divided by me plus m1, this represents mu or reduced mass of the system. Hence, in this Schrodinger wave equation, it is more better to replace m with the reduced mass mu. Reduced mass mu is equal to me m1 divided by m1 plus me, where me and mn represents mass of electron and mass of nucleus respectively. We changed mass m by reduced mass only because the hydrogen atom problem is a two-particle system and the mass is now expressed as reduced mass of the system. So, we can replace m with the mu and v by Vr in the Cartesian coordinate. So, we get Schrodinger equation in Cartesian coordinate. Now, Schrodinger wave equation in spherical polar coordinate system. We already learned about spherical polar coordinates. The three variables present in spherical polar coordinate system are r, theta and phi. R is a distance, whereas theta and phi are two angles. For the hydrogen atom problem, it is more convenient to express the Schrodinger wave equation in spherical polar coordinates. The picture represents the spherical polar coordinates. Here we can see the presence of two angles. That one is phi and the next one is theta, and the distance r, and the range of the three variables are shown here. R can be from 0 to any other higher value, and the range of phi is between 0 to 2 pi, that is 0 less than or equal to phi less than or equal to 2 pi, and the angle pi has a range from 0 to pi. That means pi has a range of 0 less than or equal to theta less than or equal to phi. This is about the range of theta, this is about the range of phi, and this is about the range of r. And finally, there is a relation between spherical polar coordinate and the Cartesian coordinate. And here this is the relationship. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. By incorporating these three Cartesian coordinate r, theta, phi, instead of x, y and z in the Schrodinger equation, we will get the Schrodinger wave equation for spherical polar coordinates for the hydrogen atom. Thus, the Schrodinger wave equation for hydrogen atom in spherical polar coordinate system is given by 1 by r square into dou by dou r of r square into dou psi by dou r plus 1 by r square sin theta, dou by dou theta sin theta into dou psi by dou theta, plus 1 by r square sin square theta into dou square psi by dou phi square, plus 2 mu divided by s cross square, 2 mu divided by s cross square, 2 mu divided by s cross square into e minus vr into psi is equal to 0. You should note the fact that 2 mu divided by s cross square is equal to 8 to pi square m by h square, because s cross is Dirac or h by 2 pi. Therefore, s cross square is equal to h square by 4 pi square. On simple substitution, we will get 2 mu divided by s cross square equal to 8 pi square mu divided by h square. So, we can use this symbol notation also. So, 2 mu by s cross square into e minus v r into psi is equal to 0. Here psi depends on three variables r, theta and phi. Hence, this is the Schrodinger wave equation for hydrogen atom in spherical polar coordinate system, and we have to solve this Schrodinger wave equation, and we have to get solutions of such equation, and its interpretation is needed for the complete study of the hydrogen atom problem. Now, we are going to separate this Schrodinger wave equation into three components, into three parts, into three simple equations, into three simple equations, and each equation being one variable, being in one variable. That is, here we are having three variables, namely r theta and phi. By keeping three variables together in an equation, it is too hard to solve such an equation, and hence we adopt the method of separation of variable to separate this equation into three equations, each equation with one variable, and after that we will get three equations, one with r variable, one with the theta variable, and one with the phi variable. The equation with r variable is called r equation, that with the theta variable is called the theta equation, and the last one with the phi variable is called the phi equation. So on adopting method of separation of variable, we get three relevant relations, three equations for the hydrogen atom problem. And we have to solve these three equations, the resultant three equations separately, and to obtain the solution. And now we are moving on to method of separation of variable. And before proceeding to method of separation of variable, first we took the assumption that the entire wave function psi of r theta phi is represented as a product of three components. The first component is r of r into second component theta of theta into third component phi of phi. I mark it as equation number 1. This is the very basic principle. Here, psi of r theta phi splitted into three components. The three components are r of r, theta of theta, and phi of phi. Note the fact that r of r is the part of the wave function which depends on small r variable. Theta of theta depends on theta variable. Phi of phi depends on phi variable. The product of three components will get the total wave function of the system. Now, this is to be substituted in the parent Schrodinger wave equation that is expressed in spherical polar coordinate. That means we have to substitute in this equation. So, the equation is 1 by r square d by dr of r square into d psi by dr plus 1 by r square sin theta dou by dou theta sin theta dou psi by dou theta plus 1 by r square sin square theta dou square psi by dou phi square plus 8 pi square mu by h square into e minus vr into psi of r theta phi is equal to 0. And this is, I mark as equation number 2. Now I am going to substitute equation 1 in equation 2. Since the first term is differentiation with respect to r square, such that I can take the two parts theta of theta and phi of phi as constant and taken outside. Therefore, the first part will be theta of theta into phi of phi divided by r square into d by dr of r square, d by dr of r square into d by dr of small r square into dr by dr plus, here we are going to differentiate with respect to theta. So, r term and phi term can be taken outside. So, r of r into phi of phi divided by r square sin theta into, now no need for putting dou, it can be taken as d, d by d theta sin theta into d theta by d theta. This is about the second term plus, here you are going to differentiate with respect to phi. So, r of r and theta of theta can be taken out. So, r of r into theta of theta divided by r square sin square theta into d square phi divided by, psi is now changed to phi, divided by d small phi square plus 8 pi square mu by h square into e minus v into psi of r theta phi is equal to 0. Psi of r theta phi is equal to 0. Now, we have to do some mathematical steps for the complete separation of variables. First of all, I have to multiply with sin square theta. Multiply with sin square theta. Each and every term should be multiplied with sin square theta. Then, after multiplying with the sin square theta, we have to divide it with theta of theta into phi of phi. We can do it in a single step or we can do it as 2 steps. For convenience, now I do it in 2 steps. So, first of all, we have to multiply with the sin square theta, and the term will be theta of theta into phi of phi into sin square theta divided by r square into d by dr of r square into dr by dr plus r of r into phi of phi into sin theta 1 power will appear in the numerator. So, sin theta divided by r square into d by d theta sin theta into d capital theta by d small theta plus sin square theta vanishes. So, I get r of r into theta of theta divided by small r square into d square phi divided by d phi square plus 8 pi square mu sin square theta by h square into e minus vr into psi is equal to 0. Into psi means nothing but theta of theta into phi of phi into r of r. So, I can put it also here, psi is equal to theta of theta into phi of phi into r of r. So, I can simply put this multiplied with r of r into theta of theta into phi of phi. In this equation also, we can put r of r into theta of theta into phi of phi instead of psi of r theta phi. Now, we have to divide this expression, we have to divide this entire expression by theta of theta and phi of phi. So, theta of theta, phi of phi and r of r. We have to divide it completely with theta of theta, r of r into phi of phi. So, whenever I am dividing it with the theta of theta, phi of phi into r of r, these two terms will vanish. So, the remaining term will be 1 by r of r into r square, 1 by r of r into r square. In numerator part there is a sin square theta into d by dr of r square into dr by dr plus these two part vanishes. So, I got sin theta by r square into, here there is a term that is nothing but theta of theta into d by d theta sin theta, d by d theta sin theta into d big theta divided by d small theta plus next term r and theta will cancel and 1 by phi of phi is there, 1 by phi of phi, 1 by phi of phi, 1 by phi of phi into r square, 1 by phi of phi into r square into d square phi divided by d phi square plus 8 pi square mu sin square theta by h square into e minus vr equal to 0. Since I am dividing throughout with this r of r theta of theta and phi of phi, that term also vanishes. Now, if we exclude one r term from here, one r term from here or r square term from here, that part contain only 5 variable. Thus, we have to multiply with the r square. Now I am going to multiply with the r square. So r square term vanishes. So the first term will be sin square theta by r of r into dr square by dr into dr by dr plus sin theta by theta of theta into d by d theta of sin theta into d by d theta by d theta plus 1 by 5 of 5 r square vanishes, d square phi divided by d phi square plus 8 pi square mu sin square theta by h square into r square into e minus vr equal to 0. And in this equation, in the last equation, it is clear that this term contain only 5 parts. Therefore, that 5 part can be separated. Now, we can separate this marked portion from this big equation as a 5 part, and that is we are getting sin square theta by r of r into dr square by dr into dr by dr plus sin theta divided by theta of theta into d by d theta of sin theta into d theta by d theta by d theta plus 8 pi square mu by h square into r square sin square theta into e minus vr equal to, this part goes to RHS, that is minus 1 by 5 of 5 into d square phi divided by d phi square. The left hand side and right hand side can now be separately equated to m square. That means left hand side is equal to m square and right hand side is also m square. So we get right hand side equal to minus 1 by 5 of 5 into d square phi divided by d phi square equal to m square. Or this we can modify it as, this can be cross multiplied here and it can be added towards the left side. So this on rearrangement we get d square phi divided by d phi square plus m square phi of phi equal to 0. This is the so-called phi equation. Now we have the phi equation like this. So the remaining part, left hand side also equal to m square. That means this part of the expression also equal to m square. Now this part contains two variables. One variable is theta and other variable is r. We already separated the phi part. So in order to separate these two equations, this part into again two more equations, we have to proceed like this. First of all, we have to divide by sine square theta. So this term will be 1 by r of r into dr square by dr into dr by dr plus 1 by sine theta into theta of theta into d by d theta of sine theta into d theta by d theta plus 8 pi square mu r square by h square into e minus vr equal to m square by sine square theta. Now we can rearrange this equation such that theta terms will be together and r terms will be together. And for that, I am transforming this part, this theta part, towards the right hand side such that I got 1 by r of r dr square by dr dr by dr plus 8 pi square mu r square by h square into e minus vr equal to m square by sine square theta minus 1 by sine theta d by d theta sine theta d by d theta sine theta into d theta by d theta, d theta by d theta. And now we are going to proceed like this. Equate LHS and RHS separately with lambda such that I get 1 by r of r dr square by dr into dr by dr plus 8 pi square mu r square by h square into e minus vr equal to lambda. And also I got lambda equal to m square by sine square theta minus 1 by sine theta d by d theta sine theta into d theta by d theta. And this part can be simplified to get the r equation, and this part can be simplified to get the theta equation. These two equations can be rearranged and simplified to get the r equation and the theta equation. Thus, the separation part is complete. This part contains only r, and on rearranging this, we get r equation, and this part on rearrangement will get the theta equation. Thus, we have completed the separation of variables. Thus, on separation of the variables, we got three relations, that is r equation, theta equation and phi equation. After the separation of variable, the three equations are like this. The phi equation is dou square phi by dou phi square plus m square phi is equal to 0. The theta equation is like this: 1 by sin theta d by d theta sin theta d theta by d theta plus lambda minus m square by sin square theta into theta is equal to 0. And the r equation is 1 by r square into d by dr of r square dr by dr plus 2 mu divided by s cross square, that is same as 8 pi square mu by h square into e minus vr into r minus lambda by r square into r is equal to 0 in a rearranged form. So these are the three important equations for the hydrogen atom problem. One with the variable phi, other with the variable theta, and the last one with the variable r. So we have to find out the separate solutions of these three equations, out of which we are focusing first two equations here. And the first part is complete solution to the phi equation. We have the phi equation dou square phi divided by dou phi square plus m square phi is equal to 0. The acceptable solution is here, where n is the normalization constant. The wave function is acceptable provided m is an integer, and the function phi must be single valued. This we have discussed previously in the case of rigid rotator and particle in a ring problem. And this can be true only if m is equal to 0 plus or minus 1 plus or minus 2, etc. The acceptable solution to this equation is phi of phi is equal to n into e raised to im phi. And this equation can be normalized to evaluate the value of n. The normalization condition is integral 0 to 2 pi phi star phi d phi, that must be equal to 1. We know about phi star is equal to n into e raised to minus im phi. Phi is equal to n into e raised to im phi. On adding together, this equation merged into integral 0 to pi n square into d phi. N square can be taken outside, that is n square into this integral d phi with the limit 0 to 2 pi, that is equal to 2 pi. That must be equal to 1 since RHS equal to 1, that is as a condition of normalization. On simplification, we get the normalization constant n is equal to 1 by root of 2 pi. Therefore, we get the complete normalized solution phi of phi is equal to 1 by root of 2 pi into e raised to im phi. This is the complete solution of the phi equation. And these are about the first few normalized values. This we already learned. This is about different few values of phi or phi m phi. Phi m phi means the value of phi depends on m, and by changing the values of m, we will get different values, and these are various values. Now we can move on to complete solution to theta equation. This we learned with the rigid rotator. We have the theta equation, 1 by sin theta into dou by dou theta sin theta into dou theta by dou theta plus lambda minus m square by sin square theta into theta of theta is equal to 0, where lambda is a constant term, that is 8 pi square I divided by s cross square. These are the conditions. Put x is equal to cos theta, and when we putting x is equal to cos theta, the limit is from minus 1 to plus 1, and if it is theta, the limit is from 0 to pi, and assuming also that the theta of theta is equal to px. This is exactly same that we have done in the previous case, that is rigid rotator problem, and we get an equation. This equation can be changed by replacing lambda with L into L plus 1 to get to the final equation, that is called the Legendre equation. 1 minus square d square p divided by dx square minus 2x dp by dx plus L into L plus 1 minus m square divided by 1 minus square into px equal to 0. The solutions of equation 1 are two types. They are either Legendre polynomials or Legendre functions. Solution of equation 1 when m is equal to 0 are called Legendre polynomial, denoted as PLX or PL cos theta, because x is cos theta. Legendre polynomials arise in variety of physical systems, and these are first few Legendre polynomials. When we put L is equal to 0, we get P0 x is equal to 1, and so on. So these are various values. And we have the Legendre equation like this. When in the Legendre equation, if m not equal to 0, the solutions are called associated Legendre functions, and associated Legendre functions are denoted as PLMX or PLM cos theta, and this is the expression for PLMX. PLMX equal to 1 minus square raised to modulus of m by 2 d raised to modulus of m divided by dx raised to modulus of m PLX, where PLX is the Legendre polynomial. We can put different values for L as 0, 1, 2, 3, etc. and m is already fixed, that is m may be 0 plus or minus 1, 2, 3, etc. Now these are various values of associated Legendre functions, and it should be noted that it is clear that when m is equal to 0, this associated Legendre function changed it to Legendre polynomial. That is very important observation. These are first few associated Legendre functions. Now, the complete solution to the theta equation can be represented like this. Theta of theta is equal to NLM PLM x or PLM cos theta. Here NLM designates the normalization constant. This function now not normalized, hence I introduced the normalization constant NLM. The term NLM is because the normalization constant depends on the quantities L as well as M, and we can normalize this function to get the value of NLM, and this is the condition for normalization. Integral 0 to pi theta of theta star theta of theta d theta, but our variable is now x. Therefore, this integral limit is changed from minus infinity to plus infinity. NLM modulus square can be taken outside, and on proceeding this integration, we are getting the normalization constant NLM equal to 12 plus 1 into L minus of modulus of m factorial divided by 2 into L plus modulus of m factorial, the whole raised to 1 by 2, or this entire term is under square root. And substituting the value of theta in the previous equation, we are getting the value of theta Lm theta. Theta Lm theta notation is because the function theta depends on the numbers L as well as M. Hence, I put theta Lm theta. And in the case of the hydrogen atom problem, it can be inferred that M represents magnetic quantum number and L represents azimuthal quantum number, details of which we can discuss in the next section, in the second part. Now, theta Lm theta is equal to 2L plus 1 into L minus of modulus of m factorial divided by 2 into L plus modulus of m factorial. This is under root multiplied with the PLM cos theta, and this is for m less than 0. If m greater than 0, the condition may change, and we are introducing a new correction factor epsilon. Therefore, the corrected expression is theta Lm theta is equal to epsilon into 2L plus 1 into L minus modulus of m factorial divided by 2 into L plus modulus of m factorial, the whole raised to 1 by 2 PLM cos theta. And the correction factor epsilon is minus 1 raised to m provided m greater than 0, and epsilon is equal to 1 provided m less than 0. Thus, in this module, we have discussed the hydrogen atom problem in the first part, and we have studied the Schrodinger wave equation in spherical polar coordinate, separated it into 3 variables, R equation, theta equation and phi equation, and now we got solutions for the theta equation and the phi equation. Now we have to cover the solution of R equation and quantum numbers and related aspects that we can do in the second part. Thus, that all about this part 1. Thank you.